Welcome back to Part 4 of Chapter 1, Scientific Thinking. At this point, we've discussed the scientific method, we've talked about how to design a good experiment, and we've discussed the differences between a hypothesis and a theory. Now I want to talk about a real-world example for why learning this is important to you. And the reason is that when science is conducted with bias, when it's conducted falsely, this can lead to poor decision-making in the population. So one really good example of this is a study that was published by The Lancet back in 1998, linking autism to the measles, mumps, and rubella vaccine. The MMR vaccine is something that all children in the United States are actually required to get before they're allowed to even attend preschool. And as a result of this vaccination, we have really eradicated measles, mumps, and rubella as being a childhood disease. So unfortunately, the lead author made a public statement suggesting that there was a direct link between vaccinations and autism, which led to pretty much a worldwide panic. And even though we're going to discuss in a minute that there's no direct evidence linking vaccinations with autism, this is still something that people believe today. And as a result, they're deciding not to vaccinate their children, which is a public health issue. So let's start talking about some of the problems with this study. So even if you just look at the study itself, first of all, there was a ridiculously small sample size of only 12 children. And the sample was not randomized because the children that were chosen to participate in the study already exhibited signs of autism. So there was an amount of bias in designing the experiment because the authors were choosing children that already appeared to have autism. There was no control group, so they didn't actually test to see if there was a difference between children who had received the vaccine and children who had not received the vaccine. So there really was no evidence of a link. The thing that was the most troubling is that after the article was published, it turned out that the lead author was being paid by lawyers for a rival vaccination company to actually make these claims. So it was hugely unethical. And as soon as this story broke, the rest of the authors on the paper actually retracted the study, and The Lancet retracted the study. But of course, nobody in the popular press really heard about this because the damage had already been done. It had already been sensationalized. And why was this the case? Well, this is where I'm going to get on a little bit of a rampage. It's because of this woman right here, Jenny McCarthy. She was popular in the 90s for being a host on an MTV show, and she had has an autistic child. So when she got a hold of this information, she went on every single talk show that she could find, making very broad claims that her son was most likely a victim of autism, and that was the way that she sort of made it sound, because she had gotten him vaccinated when he was a child. This woman has absolutely no scientific background, no biology background whatsoever, and yet everybody was turning to her as some type of authority in the popular press to speak about the dangers of vaccination. Meanwhile, tons of studies had been published showing absolutely no link between vaccination and autism. But this didn't get any time in the popular press because it was more interesting to have Jenny McCarthy, a very well-known public person, speak about her personal trials with her own son. So we started deferring to her as a decision maker in our own lives. And this is just absolutely ridiculous. So like I said, this gets me fired up because not getting children vaccinated is incredibly dangerous. This is a public health issue, and recently we've seen resurgence of measles in Disneyland out in California because of parents who had not vaccinated their children. And we've seen incidences of measles and mumps, I believe, in Europe as well because of parents not vaccinating their children and exposing other children who are not able to get vaccinated because they may have some sort of immune issue. They are putting them at risk. So it really is a matter of public health concern. And the more press there is about it, the more angry those of us in the scientific community get. So one example is a billboard that was paid for by the Anti-Vaccination League of America and friends of a particular politician who was riding this bandwagon in order to garner votes, that says the greatest lie ever told is that vaccines save lives and prevent disease. Prove it or repeal the law. And somebody spray painted over it, got polio, and this really is kind of a good point. We really have eradicated a lot of diseases that we don't need to worry about anymore because of vaccination. If people stop vaccinating their children, we run the risk of those diseases coming back in catastrophic ways. So again, being informed about the facts and the evidence about science rather than listening to what the media is saying or what other popular people who have no scientific background are saying, it's really important in today's age. So now I'm going to get down off of my soapbox and we're going to return to talking a little bit about scientific data. This should be a review for most of you who have had math before, but there are different ways that we visualize data in biology. We can use bar graphs, which use bars to represent a proportion of a value. So here we've got a bar that has a greater proportion than the other bars. And one of the things that we would need to do is sort of statistically show that that difference is meaningful. We're not going to get into statistics in this class. That really is not something that you guys need to know how to do, but just be aware that that is something that biologists have to consider. Line graphs can show connections between data points and show trends. So in this graph here, we see a trend towards something increasing. And finally, you have pie charts in which the slices represent a percentage or a proportion of the whole shebang. We tend not to use pie charts quite as much, but they can still be very visually representative. So remember when we talked about a hypothesis, we talked about how this was usually used to connect two variables together. So we may have variable 1, and we're trying to make some kind of connection, some kind of cause and effect relationship to variable 2. So in our example that we've been using this entire time, we're connecting echinacea, the variable of the dosage of echinacea, with the outcome of cold symptoms. That's our second variable. So when we design a hypothesis, we have to define these variables. We have what's known as an independent variable. This is the variable that the researcher is actually going to change or manipulate. This is the thing that we think is the proposed cause. What is causing this relationship? What is driving this relationship? In this example, that's the dosage of echinacea. Echinacea is causing symptoms to be lower. The dependent variable, just like it sounds, depends upon the independent variable. So it's going to change in response to changes in the independent variable. This is the thing that the researcher is going to have to measure and collect data on. So this is the proposed effect. This is the thing that the researcher is measuring. In our example, that's the duration of cold symptoms. So let's do another quick example. Let's say that we have the hypothesis that students, let me get my pen, that students that study more have increased grades. Really? Who would have thunk that? So that's our hypothesis. If you study more often, then your grades will be better. So I want you to take just a minute, pause the video, and write down which one of these is the independent variable and which one of these is the dependent variable. Okay, so hopefully you gave it a shot. And if you said that the independent variable was the amount of time spent studying, then you are correct, because studying is the cause. Studying causes grades to get better. The dependent variable then is going to be something like your grade point average. This is the thing that it's responding to the independent variable. Your grades will go up if you've been studying, and it's the thing that the researchers are going to measure. I do want to point out something really important. Notice that I quantified each of these. I didn't just say studying and grades. Those don't really mean anything in science. Science is something that is measured, it's something that's quantified, and so we have to put that in our variables. So it's not sufficient to just write down echinacea. We would define the variable as being the dosage of echinacea. So other examples might be levels of a hormone, amount of time spent studying, a growth rate, or the number of mature offspring. All of these are quantifying our variable in some way. So just remember that when you do examples of independent and dependent variables in your lab. So now let's take a look at how we would graph these variables and show a representation visually of the study that we've conducted. So we have our x-axis here and our y-axis up here. And what we'll see is that the dependent variable is put on the x-axis. This is the amount of time spent studying each day. And our independent variable, which here we're measuring performance on a midterm exam, is on the y-axis. And this should make sense because, again, the time spent studying, our independent variable is the cause. So we're saying if we study 1 hour every day, then we'll notice that our midterm average is somewhere around 95, right? So if we study 5 hours a day, then we notice that our midterm average is actually close to 100. Maybe that's around 99. So we notice a trend here where our grades are actually increasing in response to the amount of time spent studying. So pause your video now and take a moment to read through and answer this question. Okay, so hopefully you chose number 4, both 2 and 3 as the correct answer. If you look over at our chart here, you see that we're looking at the sex of the author, either male or female, whether or not reviewers know it or whether or not reviewers don't know it. That's our dependent variable. That's the thing that we think is the cause. Do the reviewers know the sex or do they not know the sex? And our response, our independent variable, is the number of publications written by women that are actually accepted. So hopefully that kind of helps to clarify. You're going to get some more practice with this in lab, and that is the end of part 4. We only have one more part to go.